Hello, welcome everyone. Oh wow, today we really do have a lot of friends here. Hey Mary, how are you doing? It's good to see you. And well, and Björn is here, and my friend Herman, and everybody, Dirk is here as well. Dirk from Galite, great company making VCSELs. Let's get the ball rolling. Good afternoon, Ignazio. Caro Bambino, good to see you. Let's start. Thank you very much, all of you, for joining today on a very special session of the Epic Online Technology Meetings today. We deal with my favorite topic in the world, vertical cavity surface emitting lasers, VCSELs. So let's get the ball rolling. Anna, are you ready? She looks ready. She looks full of energies. Anna has so many energies. She drinks a lot of coffee. So today is the 22nd event of the Epic Online Technology Meetings. When I took this picture with my shorts, I was very excited, but also very curious to know if this concept was going to work. I didn't know, to be honest, that we were going to be so successful. I would like to thank everyone for all the great feedback that we are receiving, or the overwhelming amount of requests to give a presentation, overwhelming amount of requests of attending, all the great emails asking to connect with each other. We are so happy with this concept that there's no way that we're going to stop, but we're going to continue with 3 meetings a week all the way to 15th of July. It's going to be a great beginning of the summer, and then we'll let you relax for the rest of the summer. Epic has now 560 members. I would like to welcome the 2 members we got in the last 24 hours, Quicks, Photonic integrated circuits from quantum computing, and Viavi. Thank you very much for joining the association. It's so great to see that every 2 days I announce new members. It's so exciting. Also, I would like to let you know that all of you here, most of you here are Epic members, so you all have access to all the market reports. We have now 17,000 view graphs for you to access. All of you have free access for this, but we purchased the market report from Strategies Unlimited, and it has several sections on VCSELs, which are extremely interested. So this is a very good read. All of you have access to this market report, the worldwide market for lasers. Have a good look at what it says about VCSELs, especially on the market of LiDAR, range finding for the defense, and the consumer electronics market. This keeps being still the largest website to find a job in photonics, www.jobsinphotonics.com. So if you are looking for a job, or if you have job openings, this is your place to go. And now let's start. VCSELs. So like in October, we had, in my opinion, the best Epic technology meeting there has been in the last 16 years. We had a meeting at Sony to talk about VCSELs with the key companies in the sector. So everybody was there, and actually everybody is here today as well. I thought that during these very difficult times, it was good to get back together again with some new friends, and also tell people in YouTube what kind of things we are doing together and what kind of things we still need to do together. So about 7-8 months after, we are here. We are here in the online world to talk about VCSELs, technology, and applications. And today we are here thanks to a fantastic group of sponsors. Optiwave, who, as many of you know, is the software tools for design, simulation, optimization of components, leak systems, and networks. A great software tool. Also, RoodMicrotec. If you ever need to test your VCSELs or your LEDs or your photodiodes, this is the best place to test your devices for reliability, especially in aerospace, automotive, healthcare. Jabil Optics. This is the company who enables the design for manufacturing in the volume production. I went to visit them in Jena. They make the GoPro camera, but they also make sure that your designs go to volume production. Ficontec. This is the company that has positioned themselves in the middle of automation for manufacturing, but in the field of VCSELs, they are enabling automation for testing at wafer level. Neumeyr technology. If you ever need any kind of diffractive or meta-optic components, this is the place to go. Even if it is for AR, VR, autonomous vehicles, all the way to consumer electronics, this is a great company for you to have in your radar. VTT, all the way in Finland, they are one of the key companies we have in co-packaged photonics and optics, and they have one of the largest R&D clean rooms that I have ever seen. And finally, VIGOSYSTEM, my friend from Poland, Czech. These guys are the best ones when it comes to mid-infrared detectors, but now they also make active lasers. And last week, they actually published their first ever VCSEL in the mid-infrared. So thank you very much, my Polish friend, Dziękuję bardzo. I think it's time to start with the person who really has worked so hard to have everybody here today, Dr. Ana Gonzalez. What's in the menu today?
Hello, everybody, and thank you, Jose, for these always nice introductions. So yes, we have a very nice list of companies that are going to talk. This is the agenda, but these are not the only companies that are in the room today. What we have here today is a very nice representation of the supply chain, as our goal is to establish new collaborations, to push technologies, and to see what are the challenges. So for this, what is important is to have a representation, companies representing each level in the supply chain. So let's start with the system integrators. We want to know about what are the challenges, what are the needs that they have in the supply chain. For that, we will have the VCSELs manufacturers to hear also about these needs. And also, well, maybe there is a need for volume production. For this, we also have companies in this level of the supply chain. And also it will be for the packaging of these VCSELs, we will require micro optics, also design software. Of course, when you go to large volumes, there are also requests about manufacturing equipment. And of course, also for the wafer level production, clean room equipment. It's very important for the packaging and assembly and testing challenges that we have here, also a representation of this sector of the industry. And well, it's more or less that's it. Just to reminder that we have here the pilot lines Vixar for packaging and assembly of photonic integrated circuits, and also the pilot line Fabulous for freeform micro optics pilot production. So that's it. Jose, if I forgot something.
You didn't. 80 companies registered for the meeting today. Some of them are here, some of them are in Zoom, some of them are in YouTube. Connecting each other is our pleasure and our life. So I would like to tell the companies that are in YouTube and also the ones in Zoom applicable as well. If you want to get in touch with any of the participants today, all you have to do is send me an email, jose.pozo@epic-asoc.com, jose.pozo@epic-asoc.com, and I will be so happy of connecting you to each other. That's what we love doing. Once again, Optiwave, RoodMicrotec, Jabil Optics, Ficontec, Neumeyr Technology, VTT, and VIGOSYSTEM. You guys rock. Let's get the ball rolling. There is no better way of doing that than to give the floor to my friend Christian Neumeyr from one of the success stories of VCSEL manufacturing in Europe, the company Vertilas. Christian, danke. Thank you very much for being with us this beautiful afternoon, at least here in the Netherlands. The floor and the attention of everyone here in the Zoom channel and in the YouTube universe is yours. How are you doing, Christian, today?
Hi, Jose. Hi, Anna. How are you?
We're doing great. As you can see, like we drank maybe a bit too much coffee, as you maybe can notice, but I think that the right amount for keeping you entertained.
All right.
If you share the screen, we'll enjoy your VCSELs.
Same for me. Can you see my screen now?
Not yet.
Not yet. Okay. All right. Should be coming up now.
It is coming and it is here. The floor is yours.
Okay, great. Well, then, thanks again for having us here and giving a short talk about Vertilas VCSEL technology. So let's get started. I try and talk as fast as Jose, so maybe I can keep the 6 minutes. Okay. Now, Vertilas is a producer and developer of long wavelength VCSELs. And that means we can do lasers or long wavelength VCSELs from 1.3 micron to over 2 micron. We have a special design. It's indium phosphide based. That makes it special because it allows us to go way beyond 1.3 micron compared to other long wavelength VCSEL technologies. We can cover everything from 17 nanometer all the way up to 2.3 micron. Today we produce on 2-inch and 3-inch wafers, and we can produce over 40,000 lasers with a current die size of 250 micron square on one 3-inch wafer. Moving to the next slide, you can see here the main applications that Vertilas and our technology is addressing today. Our biggest market and revenues are coming today from the near-infrared sensing market, mostly for technologies for tunable dyed laser spectroscopy. This is where you measure gases that are in the environment Those could be open path systems like the one shown here in this slide, where you have a transmitter and a receiver, could be up to 100 meters in distance. Applications are measuring poisonous or explosive gases on oil platforms or oil refineries, for example. And other applications are portable devices for methane detection or other gases. So very, very wide field where you need many different wavelengths to measure many different gases. The other main market are optical communications. So our lasers can address applications mostly in the data center space, intra and inter data center connections, as well as in metro networks. This is where our laser technology is able to meet the different requirements, which are in the O band for 1.3 micron, C band, and L band around 1.55 to 1.6 micron. And also looking a little bit at the performance of our lasers. Let's start on the left-hand side for the near-infrared gas analysis section. Here you can see LI and VI performance curves of our lasers. So let's start with the VI curve. So you can see the voltage on this side and the current on this axis, that our lasers usually consume less than 1.5 volt and neither maybe a bias current, depending on the application, between 5 and 10 milliamps. So the lasers are very power efficient. Same is for the communications lasers, and also that helps to save on electrical power dissipation. What's very important is for the gas sensing market is the tunability of the laser. And as you can see here on this chart at bottom left, that you can tune our lasers with the bias current. So by setting the bias current to a certain point, operating point, you can actually tune the laser. So in this case, you can tune it, for example, from 1651 nanometer all the way up to 1655 nanometer. And that allows you to scan across so-called absorption lines for the sensing market. Now for communications, our lasers have the fastest lasers have a S21 3dB bandwidth of around 17-18 gigahertz. And it has been shown that our lasers have been modulated up to 40 gigabit per second on-off keying. Of course, you can also do this with DMT or other kind of modulation formats. These are very nice single mode lasers. So you can see bottom right, we have typically a side mode suppression ratio of 40 dB and more. And then the concluding slide for this talk is our outlook and the roadmap, what we are working on in other applications. I'm starting here with the high power two-dimensional VCSEL arrays. So we have developed prototypes with over 1,000 emitters on one chip, allowing us to have several watts of CW power in modulated operation, pulsed operation. This can be a multiple of that. We are also working very actively with partners all over the world, and especially in Europe, for example, with VTT, to integrate our VCSEL technology with silicon photonics chips for very high data rate, very highly integrated silicon photonic integrated solutions. The other activity we are following is to develop also long wavelength VCSELs, but based on gallium antimonide materials. But it allows us to also go beyond 2.3 micron. And finally, we have also developed prototypes to have a wide tunable laser, which can be tuned over 100 nanometers with the MEMS VCSEL approach. Okay, so that concludes a brief overview about Vertilas and our long wavelengths indium phosphide VCSEL technology. Thanks a lot.
Thank you very much, Christian. Oh, wow, just on time, right? Very good. You really put the timer. Thank you. Okay, so maybe, Christian, this is a good moment for you to comment more about your role in Passion, about these amazing VCSELs that you are doing in all the C-band.
Okay. Yeah, in Passion, we are developing like a terabit integrated solution. It's a single chip with 2 terabit of throughput. And we supply VCSELs in the C-band to cover over 40 channels in the ITU DWDM grid. So we are the supplier of the laser technology. So we supply 40 different wavelengths, which are integrated on a single silicon photonic chip from VTT. So it's a very, very exciting technology, highly integrated. It's more like a chip technology solution, but for optics.
An amazing technology integrating the 40 pixels in the same transceiver. So yes,
Yes,
amazing. Yeah. Okay, so we have a question from you from the YouTube channel. Okay, this question is from Phonics from Reza Maran. What is the present achievable wavelength tunability range for telecom, and what is the plan to increase to this range product?
Sorry, I'm not sure if I fully got the question. So what is the wavelength range that we can cover? Or
the wavelength tunability range for telecom.
Wavelength tunability range. Well,
yes.
If you have
any plan to increase this tunability?
Yeah, today with our, let's call it the standard VCSEL approach, we can tune several nanometers. So meaning if you tune like 3 to 4 nanometer, you can cover several ITU channels, depending if it's a 100 gigahertz grid or even smaller. But we have this MEMS VCSEL approach, so we try to tune 50 nanometers up to 100 nanometers in the future.
Okay, yes. I hope this answers the question of Reta. And we have a second question in the YouTube channel from Antonello Vanuzzi from Photonics 42. What is the development status of single mode VCSELs at 5050 nanometers? 1550 nanometers. Okay, so these are very qualified.
Yeah, we are in the final qualification phase. We have HTOL data of over 40,000 hours, and we have accelerated aging campaign with over 10,000 hours. So our goal is to fully qualify and finish qualification in 2020. And then start regular production towards the end of this year.
Okay, and last question from Antonello. What are the market requests for these 1550 nanometers pixel?
For communications applications?
Yes.
Okay. Well, to cover several ITU channels, to have certain optical power. Especially also at high temperatures, but we can supply sufficient power of around 1.5 to 2 milliwatt, even at 80 or 90 degrees. At 50 degrees, the lasers have about 3 milliwatt optical power. What's also important is the data rate. So we have 2 product versions. One is for 10 gigabit, and the other one is for 25 gigabit and more. And the side mount suppression ratio of 35 dB or more. So those are the key requirements in a very low power consumption.
Okay, and then we have a few questions also here in the Zoom chat for you. What a success, Christian. Okay, so we are from Domenico Cuside. Maybe you are here, right, Domenico? Maybe you want to make the question by yourself.
Well, I mean, actually, I've been in contact with Christian in the past. So, well, I mean, we would like to discuss a little bit more in details these single VCSELs that he is developing for a quantum communication application that we are developing. So, the question is if it's available for a further discussion.
Okay, sure. Yeah, I mean, this is a new market for us, and we can discuss the requirements. And then hopefully we have the right laser for this type of application.
Okay, thank you.
Domenico, you joined this meeting with a very clear goal. You have a demand for a VCSEL for a particular application. You want to share some of these specifications with the people today? There is no better audience than this one.
Well, let's say, I mean, what we are using is a laser. So since we found some niche application related to what we are developing, which is quantum random number generation for some quantum application. I cannot give more details, but in the past I've been discussing with Christian, but at some point let's say the conversation ended. So I would like to restart this conversation if it's available.
Okay, perfect. So we have more
Thanks.
questions here in the chat. Photon design, Dominique, are you here, right?
Yes. Hi.
How are you doing?
Yeah. So thanks for that talk. You seem to be doing great things with your VCSELs. Yeah, I was impressed. You said your VCSELs are single mode. That usually makes them inefficient. So what is the differential quantum efficiency you achieve in single mode regime?
Well, I wouldn't say that having a single mode laser makes them inefficient. It's a trade-off between the optical power that you get from your device and the single mode performance. Of course, if you have a wider active area, you can get more optical power. But typically, our wall plug efficiency is in the range of 15 to 20% roughly.
Okay, thank you.
Okay, and also Optiwave have a request.
Yes, actually, I'm just asking about the data because our software tool has many, I'm going to show it later on, many components which model VCSELs. And we hope that we get experimental data to be able to implement it and give better modeling for these VCSELs. So how open to share data with us.
Okay, yeah, I think we need to talk about the details, what we can share. If it's just like measured data, of course, there's no problem to share that. And I would probably hope to understand a little bit more about your modeling. Is it more thermal modeling or is it behavioral modeling? So what is the output of your simulation or your tool?
Yeah.
Are you analyzing the electrical performance, the optical performance, or is it, going even so far that you can show how the laser performs in certain applications? I think that would be interesting to discuss.
For sure, this will be very interesting to discuss offline, okay? Because you are getting more and more questions. And okay, Sergey, so you have a request? Sergey from Osram?
Yes. Hi, Christian, thank you very much for your presentation. I just have a technology question. Are you limited only to single emitters, or can you offer arrays? I mean, and this is a little bit related to ineffectiveness. So this is how you make these things. If you combine those, you can make them more powerful.
Absolutely. So if I maybe jump back to my, I don't know if that's still visible. If I jump back one slide, you can see here a two-dimensional array that we had over 1,000 emitters on one chip.
Oh, okay. I missed that.
Yes, the answer is yes, we can do arrays. We can do a one-dimensional arrays like for optical communications, like for 10 channels, 12 channels, and for parallel interconnects, for example. Or for more powerful or high power applications, we can have VCSEL arrays, two-dimensional VCSEL arrays, and they can either, the emitters can be addressed either together, so they all emit light together, or we can also have like certain parts of the chip being addressed separately. So everything is basically possible by design.
Very good. Make sure that I make for you an introduction after the meeting, okay? So you can discuss more about this. Very good. So yes, there are more questions. Wilfried from RoodMicrotec.
Yes. So may I talk or?
Yes, please. Go ahead.
We had a European project before with Vertilas. It was a very nice, successful project. We liked it very much. At the time, I remember you were more on the component side. It seems that you are now also going towards sub-assemblies, or is that true, or is that still more on your client side?
Okay. Yeah. Okay. Yeah. So yeah, thanks. Yeah, that was a very interesting project we worked on together. Yeah. And you're right. So Vertilas is mostly a components company. So our core competency is really the design of lasers and the manufacturing and testing of the lasers. But we are also more and more getting into the assembly techniques, because especially together with silicon photonics, we really need to fully understand the requirements. So we have packaged lasers in more regular TO type packages, for example, what we offer today, or LC TOSers, like transmit optical sub-assemblies for SFP plus modules, or for pigtail applications, fiberized applications. But we are also now working with partners to offer like maybe optical engines in the future, at least have a reference design so people know how to take our lasers and integrate them with silicon photonics in the future.
Oh, okay, very interesting.
Christian, you got the record of questions so far. It's quite impressive. 2 more potential partners for you. The first one, Sumitomo, my friend, my very good friend Shikata-san, is wondering, does your VCSELs of 15 nanometers, do they have enough power for the ADAS market, for the automotive market?
You mean automotive for LiDAR applications?
He mentioned ADAS, but I guess LiDAR, yes.
ADAS, I'm not familiar with ADAS, but LiDAR. Well, LiDAR are 2 types of applications. One, as far as I understand, is more the long-range applications where you need a lot of optical power. And the VCSEL technology may be borderline to have enough power, but there's also near field or near range LiDAR applications just around the car, as well as inside the car. And for those applications, our lasers certainly should have enough optical power, especially if we do 2-dimensional arrays.
I will introduce you to Shikata-san in a separate email from Sumitomo. You guys need to speak. Another question from Sun Microsystems. Farsad is wondering, do you develop also the electronics for the VCSELs?
No, we don't. Of course, we test our lasers in our applications lab with laser drivers from commercial vendors. But today we do not develop our own electronics. We are really an optoelectronics company focusing on the laser technology.
Okay, very good. So then, that's it. Let's move forward with the program and let's go to the second speaker of today. So it's my pleasure to introduce you, Julien Boucart from 26. So
Thanks,
Julien,
Anna.
hello.
Yes, hello.
So
Hi.
if you want to share your screen.
Yes.
Very good.
Can you see my screen?
Yes, and now you can go to the presentation. Yes.
It's good? Okay, good. So thanks a lot for giving me the opportunity to talk to such an interesting forum. I was already in Stuttgart, and as Jose mentioned, this was already super interesting. So I'm hoping that it will match to the same level. So I'm working with the company 26, and we're a supplier of VCSELs for all kinds of application, data communication, industrial applications, and consumer. So today, the talk I will give is really focusing on the consumer application, and even more to focus on the mobile application. And what are the attributes that you want to bring, or that you want to develop your VCSEL for, in order to match the mobile requirements? So I will start from the technologies. There are different ways of looking at the problem, but one of them is to start from the technologies. And let's say, roughly said, there are 2 main categories. There is time of flight based, and there is triangulation based. So if we start from the time of flight based, they tend to be used in applications such as augmented reality, bokeh effect. So that's the blurring of the background when you take a picture, so that the subject pops out. Autofocus, virtual shopping. And even then, they branch out into 2 subcategories. There is direct time of flight, where you really measure, you send a pulse of light, and you directly measure how much time it takes to come back. But then you have to see that because you rely on the speed of light, the electronics requirements is very demanding. You need fast modulation, you need fast detectors, and to give you the order of magnitude, a round trip at 1 centimeter is 67 picosecond. So the electronics needs to be incredibly fast. And then there is another way to measure this time of flight, this depth information, is instead of measuring directly the pulse of light round trip time, is to measure the phase shift, for example. So you will modulate the light with a known modulation pattern, and you measure by how much the phase is shifted. So you kind of remove or reduce the requirement on the modulation, because now you're only looking at the comparison of the phase shift on the modulation signal. So you're still pretty fast, but not as demanding as what you get in a direct time of flight. The advantage of a direct time of flight compared to an indirect time of flight, I'll talk a bit about it now and I'll talk about it later as well, is the fact that in direct, you get rid of the thermal effects. You tend to want to have a very high peak power, so very high peak power in a very short pulse, and then have a long duty cycle, low duty cycle. So a long pause between the two pulses, which means that really there is almost no thermal effect. And what does it mean for a VCSEL is that when you get rid of the thermal, you can actually get more power out from a certain unit area of semiconductor. So you can overdrive the VCSELs. So it has advantages because then all of a sudden you have a high peak power that competes against the ambient sunlight that you see here, which is present in all mobile application, and you improve your signal to noise ratio. So direct time of flight, because of those advantages, is still very interesting despite the demands that you have on the modulation on the electronic side and on the sensor side. So in general, time of flight, they have advantages and disadvantages. The concept is very simple. Send a pulse of light and you measure how much time it takes to come back. So from the software side, it's not very demanding. So it's a simple software. That means also that all the architecture, the computational requirements is not so high, which also reduces the thermal load and the energy load on your mobile device. Also, and that's in contrast to the triangulation method, you don't need parallax. That means you can have a compact illumination and sensor. They can even be in the same module, in the same subassembly. And you can make all together the solution very compact, which is very attractive for a mobile device. Another feature is that as you go further out to measure longer depth, the noise only increases linearly. And that's in contrast also to the triangulation method where it increases quadratically. So that's why in the application, time of flight tends to be used for long range. That means world facing. That's what I described earlier, the augmented reality, the bokeh, autofocus, that's all world facing. On the other hand, there are some disadvantages, and one of them is that it requires a dedicated pixel technology. You cannot use your standard CMOS sensors, and those pixels are not as mature, and also they tend to be big. That means that altogether the sensor you will get have a lower spatial resolution. And that also drives the use of the time of flight technology into different applications. When you don't require high resolution, but you need long range, then you will find time of flight. A contrario, when you need high spatial resolution or short range, then you tend to find structured light. So now going into the structured light, you will see why there is this dichotomy between the two. In structured light, it's similar to stereo vision. Stereo vision is the same as our human vision. We have two eyes. And from the parallax, the fact that we don't look at the target with from the same position, so there is an angle, there is an offset angle. So we convert the depth information into a spatial shift. So that's stereoscopic vision. And structured light is very similar. Instead of using two detectors, the two eyes, you have one illumination source which projects a known pattern, and the other, the detector, is looking at a parallax and is looking at the shift of your known pattern. And from the shift of the known pattern, it can infer the depth information. So the advantage here is that it uses standard CMOS. So you can get very high spatial resolution. The depth resolution can be very good, but it doesn't have to be. It's related to the distance between the detector and the illumination. And the reason is because you want to have high angles. So high angles correspond to large spatial shifts. So it's an advantage, but it's a disadvantage. That means you can get good spatial resolution, but that means that in order to get any depth information, you need to split your illumination and your sensor. And that means that you cannot make a compact system anymore, which is a disadvantage for mobile applications. The other thing is that this baseline, this distance between the illumination and the sensor is very critical. That means you need to know it at any given time. So the assembly for the illumination and for the sensor needs to be very robust, and you need to monitor it. On the reliability side, because the pattern is used to get the depth information, if you use a VCSEL emitter as your dot in your pattern, if the VCSEL emitter is dying, you lose depth information, or with the context of its neighbor, you lose its depth information. So the requirement on the structured light system on the VCSEL is much greater than in a time of flight. In a time of flight, one emitter is part of a collective of several hundreds. So if one emitter dies, well, you get a bit less power, but then you can crank up a bit the current, and then there is no difference. You don't lose depth information. So you see that already by choosing the technology, it has different requirements on the illumination source. So if we go a bit more generic and we look at what do you want from the VCSEL? You want it to be small because you want to make a compact system, and small, still you have the requirement, let's say, on an output power because you want a certain reach. So you want to increase the optical power density per unit area. You want it at low cost, of course. That means that in general, we'll also try to drive the size down. But again, you want to increase the power per unit area there. The reliability is very critical. And that's not only for structured light, as I talked about it, but even for time of flight. You want to push out the wear out, the end of life of a certain VCSEL array to well after the product lifetime. The modulation speed is very important, not so important in structured light because it's pretty slow modulation. But as you get to direct time of flight, you want to be able to have very short pulses. And something that is also important, and especially in direct time of flight, you want to get as much power out, so you put a lot of current through. And the current drives electromagnetic radiation. So how can you reduce this electromagnetic radiation in a compact system such as a mobile phone? And the power efficiency of your VCSEL is directly driving battery life. So it is very important. But it will also drive the heating of your VCSEL. What you don't convert into optics is converted into heat. Then the beam shaping is something that you want to match the output of your illumination module to the camera system that you're using. So you want to have a good matching between the two systems. And finally, last but not least, is the eye safety. It's a mobile device. It will be used in all kinds of conditions and operations. It needs to remain eye safe 100% of the time, not 99.9% of the time. So in terms of the products that are offered, depending on this on the applications, we have, for example, for display navigation, that's what we use in the mouse. So that's not mobile, but it was used in the BlackBerry to navigate the button. So it's a low power, 850 nanometers. It's a single mode device, polarization locked. Then there is the whole category of Internet of Things, which tends to be indoor. And there, because it's indoor, you want to benefit from the 850 nanometer sensitivity on the receiver. That's why they tend to be at 850 nanometers. Then you have the single emitters or low emitter count for proximity sensors or for autofocus. Those are mobile applications, so they are 940 and they're 5 to 20 milliwatt. They can be single mode or multi-mode emitters. Then you have the whole category of time of flight, and that's indirect and direct time of flight. And like we heard a bit before from Christian, you can aggregate power by putting many emitters, and that's what we do. So we scale the size of the arrays to match the power requirement. And then we talked about it a little bit earlier from the question from the gentleman from Sumitomo. You can also get to ADAS or LiDAR, so assistant driving. And that requires powers that are much greater. So I put more than 25 watt, really it can go up to kilowatt level. And that's where direct time of flight is definitely a technology of interest. And I think I exceeded my 6 minutes, so I will probably stop here.
Thank you very much, Julien. Actually, having met you in Stuttgart was one of the highlights of my last year. It was great, the amount of connections that I made with you, and you followed up with all of them. So on behalf of the 500 members of EPIC, we love to have you. At EPIC. We have a lot of questions, but the first question is the EPIC question, Julien. What can you do for them? What can they do for you?
So what we can do for them is fairly easy. We can make VCSELs. So as soon as you have a demand for VCSELs for direct time of flight, indirect time of flight, consumer application, even datacom, I'm not talking about it, but we're there. And we can customize as well solutions for your problem. What I'm looking for is, for example, on the direct time of flight, there is still a lot to be learned. We're exploring the regime of the overdrive. And so there it requires fast electronics, it requires fast testing solutions. So here, I'm interested in understanding the ecosystem around direct time of flight and the partnerships that we can form around this characterization of this mode of operation.
Excellent, because we have a lot of questions of people who want to work with you. And the first one is from a company that I love, Optics Balsers. Whenever you're looking for filters or coatings, don't go any further. The question is from Reto Keller. Thank you very much for being with us this afternoon. Reto, how are you doing?
Thank you, Jose. I'm doing very well. Thank you for organizing these events. They're very helpful to bring the industry together, and even despite quarantine, get in contact with a large customer base. My question is regarding eye safety. Julien mentioned that it is extremely important to maintain power levels of the VCSEL to ensure eye safety. My question would be, is there some feature that comes with your VCSEL package to address that, or is it up to your customer to solve that into their modules, let's say?
Yes, that's a good question. So we are supplying VCSELs in different forms. We can supply chips. And in general, it tends to be that chips by themselves are not eye safe. You can put enough current into them so that they become not eye safe. That means it needs to be guaranteed at the next level. We're also providing packages. And on the package side, we provide a certain level of eye safety, but it cannot cover all the corner cases. So for example, we'll put a diffuser, and the diffuser in normal mode of operation will be eye safe. But if something gets damaged on the diffuser, then it still might not be eye safe. So it still needs to be guaranteed by the end customer.
Okay, excellent. Thank you for this answer. We're actually working in this area, and we have a couple of coating solutions. For example, ITO or metallic conducting coatings that we can pattern to very small feature sizes. And we do see that in commercially available VCSEL packages, such kind of features are integrated. And if you're looking into such solution, you're welcome to contact us on that.
I will introduce you. You have to talk to. But first, I'm going to go to a beautiful city in Germany, Karlsruhe, because I think Nanoscribe can 3D print some micro optics for you. Jörg, how are you doing today? Hi, Jörg from Nanoscribe.
Yes, I'm
in the
doing
room?
fine.
Yes.
Yeah. I just needed to find the right button.
What's your question?
You're always too fast. Yeah, I have a question. What I was running since the last meeting. Hello, Julien. Nice to meet you again. Was again a very interesting and good speech or presentation this time, rather. So my question is mainly on time of flight, distracted light. What are the beam shaping methods which are used right now? What are the trends? I mean, this is linked to the camera model, so it's getting smaller. What do you see for trends? Do you see them at your side, or is it more in the next step in the production?
Yeah, I would say I don't see that the trends have changed that much. So we still use diffractive optical elements to shape the beam. So that would be typically diffusers. There are still the request once in a while for structured light solutions. So that would be more for a dot generator. But you're right, it's probably more at the next level that they would have more insight into the beam shaping.
So you're not integrating beam shaping directly into the VCSEL?
Directly, well, we can talk.
But later you're going to see the presentation from Vixar and you will be amazed, Jörg, because we're going to go now to Belgium. I feel a bit like Eurovision these days. I go to Belgium from Germany. I go to a company called Umicore, which is one of our biggest material suppliers at Epic. Bendix, how are you doing today?
I'm fine. Thank you, Jose.
What's your question?
Well, I know VCSELs, you need a lot of VCSELs to get to high power for LiDAR. Are they ever going to be price competitive, cost competitive with edge emitting lasers?
Oh, that's an extremely good question. I'm actually in the process of assessing that. I think in the end, if you just need raw power, it would be very difficult because the fill factor of an edge emitter can be much higher than of a VCSEL. Let's say on an edge emitter, you can get 80% of the semiconductor area that's emitting light. On a VCSEL, maybe you get 20%, 30%. However, there are some features of the VCSEL, for example, the vertical emission, the wavelength versus temperature, the modulation speed that make it that it can be attractive. But I would probably agree with Christian's statement that long range, probably more edge emitter space, and short range, maybe that's where VCSELs can play a role.
And I go now to the company VIGOSYSTEM. Nick Ledenshoff is with us, the fastest VCSELs I have ever seen. Nick, how are you doing today? Nick from VI, I think we have you here. Yes, here. Nick? I think we are not hearing you, so I'm going to ask the question because you post in the chat. How do you check for eye safety? Is 20 milliwatts and 5 nanosecond mentioned in the presentation the limit for 940 nanometer VCSEL arrays?
No, you cannot answer in absolute like that because it's not only about power and pulse length, it's also about the divergence. And it's also about, well, in this case, the wavelength. And you also have to think, is there any focusing element somewhere in your optical train? To be honest, I cannot answer in absolute whether it's 20 milliwatt, 5 nanosecond. What I say is that the method that we're using is to place at 10 centimeters an aperture of 7 millimeter, which corresponds to the iris of the eye. And then we check for the power density on the surface that replicates the retina.
Well, one of the most beautiful debates that we had at Sony was this one about eye safety, and that was spectacular. It's all recorded. You can find in the Epic extranet. We go not very far away from here, actually very close from here, just behind these roll-ups, the European Space Agency. Simone, thank you very much for joining this afternoon. What's your question?
The question was simply just, is there a way to extend the wavelength from 940 to, in this case, 956 at high power and with preferably with a single mode?
So the short answer is yes. There is nothing so specific about 956 that it cannot be done. It's just that we don't do it. It's not part of the standard wavelength range. I mean, it's the standard wavelength range. It's not the standard wavelength. But we have, for example, VCSELs at 980. We have VCSELs at 960, 940. So 958 is nothing special.
Okay.
In terms of single mode, same thing. The same technology that you apply at 940 for single mode can apply at 958.
I have a few questions in the YouTube channel as well. We're going to go very quickly through them. The first one is from a company that we all love, Keithley, Tektronix Keithley. They're wondering about the application requiring high current level for pulse driving VCSELs and how much is such current?
If you go into LiDAR, we can talk up to 500 amp. So we're talking really very high power. There are solutions where you can reduce the current and increase the voltage instead. I think it will be talked about by the talk from Osram, Vixar, sorry. In general, for consumer, maybe we're talking of 20 amps.
Next question is from ST Microelectronics, Eric Masarella. He's wondering, do you have any plan to produce long wavelength, more than 1 micrometer wave VCSELs?
This is something that we look at, so we monitor, and that's why it's also great to be in this meeting to see the work from Vertilas or others.
This one is actually a tricky one. Can VCSEL in arrays be selectively turned off?
Yes. So they can be addressed all in parallel. That's the standard way that arrays are made, but you can also dedicate dedicated lines so that you can address each single emitters. The drawback of that is that it takes real estate, and real estate costs money. So that means you have a bigger chip and it will cost more money.
I think you are fighting with Christian to see who asks the most question. I think it's a draw. It's really a draw. And we go to the next Epic member. We go to Jabil. We go all the way to Jena, where they actually make the design for manufacturing into optical modules. And I'm so happy to have Simon in the room with us. Simon, the floor and the attention of everyone is yours. It's a great day for collaborations.
Thank you, Jose. Very energizing talk so far. Let me see where I can start. I'm taking the discussion to a slightly different level, just more on the system level. So we are integrating not only VCSEL emitting different light sources into various systems and taking those into mass production. So I picked a specific application here. It's a consumer application. We have the general task to design smart and small dot projector modules. And principally, the way it's been done, you have a light source which is defined by a number. By the number of emitters, the beam parameters, and you end up with deciding between edge emitters and VCSELs. Then, of course, you have some lenses built into that system that define dot size, the angular spread, and the depth of focus, basically. And this beam delivery goes usually into diffractive optics, that define the dot number, the dot density, efficiency, as well as the energy distribution. And finally, that's what then customers and system integrators are interested in, is the dot pattern. There are the requirements regarding spatial distribution of all the dots and of course, energetic distribution of the dots. This is all accompanied by the acceptance of distortion, which is always different from system to system. So that's kind of the basic setup, general design task. And as we are talking about the first portion here, the light source, let's elaborate a little more in detail on that one. This is one of the designs of a dot projector module, which we came up with, consisting of different cameras, NIR, RGB cameras, and the laser protection module in here. The conceptual setup I showed you already the slide before. And looking into detail, we have here the EEL, the edge emitting light source, the prism, optics, etc. So that's the currently used mass production setup. And as it is a near field application, so closed operation mode, we are considering VCSEL. Why are we doing this? We consider those to be available in higher power. You have the possibility to set up arrays of VCSELs and go into the hundreds of milliwatts. That's what we are looking for. Plus, you have the option to operate in pulsed operation, which increase power as well. What we found interesting is the wavelength stability, which is compared edge emitter at 0.3 nanometer per Kelvin compared to VCSEL, which is 0.06 nanometer. So it's a lot more stable. We see a higher sensitivity and the possibility to have a very narrow spectral line width, which is important also in the applications we are serving. From a system design view, of course, you have the edge emitter on the right, which is a side looker, and you have the top looker, the VCSEL. I saw that Vixar is also presenting today, so I stole this, but the reference is down here. You can direct the projection that is possible, and of course there's a lower power consumption on the VCSEL side, which is especially, but not only limited to consumer application, very important. So how does, from a conceptual setup, a VCSEL-based dot projector look like? You have, of course, the VCSEL array in this case, combined with a microlens array. So the collimation of each VCSEL emitter separately by a corresponding micro-optical element. The micro-optical elements could also be stacked directly to the VCSEL array. That's also a possibility for optimization, which allows a more flexible access to new design concepts in general. Next level is the DOE, the diffractive optical element, sometimes combined with the Fourier lens. So in this setup, the DOE acts as an optical grating, influencing the optical spread, depending on, of course, the period. The field of view depends on the feature size and gradients of the profile, and the energetic distribution then depends on the height profile of the period. Fourier lens can be implemented, don't necessarily need to be. That's depending on the angular spread that is desired. So talking about the dot pattern, I have to move you, Jose. The dot pattern is a replication of the VCSEL arrays in the image, in the detector plane. And there you can see already a lot of optical effects that we are being faced with, and that need to be compensated or eliminated. And to illustrate this, here are a few more images. So the working range is decisive in this system. If you look at 200, 600, and maybe 1000 millimeter working range, you need to decide where you optimize the system. In this case, it's optimized for 600 millimeters, and there you come across so-called tessellation effects that originate from the finite extent of the VCSEL source and depend on the working range in the overall system. Of course, there is know-how required to compensate for those tessellation effects at the required working distance. In this case, it's a 600 millimeter optimization. Of course, for the other distance, and still the effect is existent. So that's needs to be taken into consideration. There are also additional considerations we are taking when deciding about utilizing edge emitters versus VCSEL. The arrangement of the VCSEL offers flexibility regarding the point cloud. I mentioned that a few slides before. Distance needs to be used for the separation. Focal length of the micro lenses influence the definition of the divergence. If there's a small low divergence or system level, you basically look at a good collimation for a good point separation, which is decisive for the detection afterwards. And last point here, which is a very important one, is that custom design of VCSEL arrays are required. Of course, there are vendors out there for standard designs, but we are at Jabil sometimes looking at custom designs, and we see increasing need of a close cooperation of optical design, the VCSEL manufacturers, and of course the software providers to provide best results. That's the few information I wanted to give on the technology side. Looking at applications, of course, there's a huge number of different applications. I focused on the ones that we are mainly involved in. So face ID, gesture recognition, 3D sensing is something we are highly involved in. Distance sensing, automation control, LiDAR, so it's both automotive as well as industrial LiDAR, and robotics in that case, driver monitoring, collision avoidance, heating systems. Very different application, but also very interesting. And a few designs mentioned here that we have already taken into mass production or volume production is illumination for driver monitoring cameras, light sources for 270-degree time-of-flight camera system, and floodlight illumination for 3D sensing, which I showed before in the picture. Yes, a few words about Jabil. Who's known, Jabil is quite a large corporation with $25 billion revenue. We are taking components and sub-assemblies into system level and take them into volume production to serve customers worldwide. Thank you very much.
Okay, thank you very much, Simon. So, and now maybe you can summarize what are the challenges that you are proposing to these companies, or how these companies can help you.
The challenges are manifold. Talking about the VCSEL itself, of course, the customization in terms of wavelength and power. So we are also looking at higher wavelengths like 1300 nanometers, while maintaining a good portion of power on that side. And also the software part, not the software part for optical design, but the software part on the system level. That's something that we tend to cooperate with.
Okay, so the companies in the room will be interested in collaborating with you.
That would be great. To answer your second question you might have, is that even though Jabil is focused on the high volume, we see that the photonics market is highly fragmented. So there are a lot of small companies, or many companies in niche applications. We have capabilities here in Germany, in Jena, to incubate such kind of business on a prototyping, low volume assembly capability to incubate until it's ready for mass adoption, mass volume production adoption. So that's something that is maybe interested for the guys attending today. So Jabil, don't be scared of the size. We can also look into smaller volumes, high mix. But of course, there needs to be a good outlook, a good business case for higher volume.
Okay, thank you. And we have a lot of questions for you as well. So first of all, Björn from SABIC.
Yes, hello, Simon. You are looking for cooperation or support in optical design. Which kind of lens material do you consider?
So if that impression has been made, that we are looking for cooperation on optical design, we are very well set. We are Jabil Optics in that field, so we have a lot of design capabilities in-house. We have a few partners that we work with, but this is not a key area. But your question is, we basically handle glass polymers, so we are independent from the optical material. We can handle all of it, and we are actually highly involved in all of our designs to work with innovative materials.
Okay, Simon, then I will come back to you with our XTEM grades, thermoplastic grades, which can even be used in reflow soldering.
Okay.
Be a very interesting alternative.
Okay.
Okay, so let's make sure that I make the introduction after the meeting. And Jörg, from Nanoscribe, you have another question, right?
As the building space is getting smaller, is the angle out of the DOE something which is critical for you? Reduced angle or things like this?
For the moment, we feel that this is a manageable task, but since the system sizes continue to be decreased, it's on a decreasing scale, that might become an issue. So if you have ideas and input from that side, that would be interesting.
I think we have already exchanged cards last time. I'm not sure at Tyrion or in Sony, so I'll get back to you.
Okay. No, I was at Tyrion in the Netherlands.
Then
yes.
it was there, yeah.
Okay.
Yeah. Bye.
Okay, and we have another question from Nicolas from Aarhus University.
Hello, this is me. Yeah, I had a question concerning your choice for laser. You mentioned somewhere that you consider narrow spectral line widths, and I was wondering what typical line widths or frequency noise you need for your applications.
That's a very good question, but I need to answer that in a separate chat. This is subject to some limitations in what I can reveal here.
Okay, yeah.
But so far we have been satisfied with what is available from companies like II-VI and other vendors, but there's a trend to look into this in more detail.
Okay, maybe I'd be happy to have an interaction with you. Here in Aarhus, we're setting up a new research lab, actually, focusing on narrow line width semiconductor lasers.
Okay. Yeah, I think the way is always through Jose
okay.
here, and he has all the contact data.
Wonderful. Well, nice to meet you, by the way.
Thank you very much. Nice to meet you too.
Jose for doing the introduction. Very good. Okay, and we have another question from EB Group, Martin.
Hello, everybody, and yeah, thank you for that nice presentation. I was wondering, and Jörg started already this question also a bit, how about the form factor requirements? We come from the wafer level manufacturing, and we do a lot of lens molding and wafer level assembly, and we see here a big drive for the new VCSEL technologies. However, when I look at the design you showed, it seemed to be bigger and more single lens assembly. Is this correct, or you also work towards wafer level assembly?
The design I showed is of course a little aged. The latest one we have developed I cannot show you here, but of course there's always the desire to decrease size, and wafer level technologies in all respects of importance to us. So please feel free. I think from one of the previous meetings I had a brief look at your website, but it would be great to talk in detail what you offer.
Yes, we can talk about this. I'll give you my contact.
Thank you.
Thank you.
Okay, very nice. So let's move forward with the next presentation. So it's my pleasure to introduce you Mary Hibbs-Brenner, CEO at Vixar. So Mary, I will be sharing, now this is the first time that I share a presentation. Okay, so I will be sharing your presentation.
Okay, thank you.
Okay, and now, okay, just tell me when I have to change the slide, okay?
All right, well, great. Thank you very much for organizing a way for us to meet together even in these times. Vixar is a subsidiary of Osram, and we make a range of VCSELs that go from the red around 660 nanometers up to 980. We also have a single mode, single VCSELs up to large arrays of multi-mode devices. And so today I'm going to focus on VCSEL illumination for 3D sensing, and in particular I'm going to talk about the time of flight applications. So the next slide, please. So everyone's aware that VCSELs were first incorporated into mobile phones by Apple, and their approach was to use a structured light approach. In More recently, time of flight has been adapted, particularly in some of the Android platforms like Huawei and Samsung. And Julien provided a nice overview of what the requirements are. Some of the applications are starting to propagate into other areas. So, for example, in the consumer market, there's interest in putting 3D sensing into AR and VR systems to be able to add sort of situational awareness. In the industrial market, 3D imaging is being used in things like autonomous delivery vehicles, robots in warehouses, and drones, and also in sensors for safety systems. And there's also now design activities going on to put 3D sensors into the automotive, both in the interior, where they're being used for things like occupancy sensing, driver monitoring, gesture recognition, as well as the exterior. And that's more the LiDAR regime, where the distances that one is trying to sense are much larger. But there's a whole range in the exterior, from things kind of around the car to long distances in front or in back. And so, as was summarized before, in the consumer market, it's really power consumption and size that are critical. When you get to the longer distances now, the need is not so much for size, but rather for very high peak power and minimizing the drive current. So the next slide, please. So I'm going to focus on a couple of things that advances that have occurred over the past year in the time of flight 3D sensing. On the left side is more of a consumer solution where the size is key. And one of the developments has been to make integrated illumination modules that incorporate multiple different features. So of course it has the VCSEL, a high efficiency VCSEL, but a driver chip is now being incorporated into the same module. And that not only helps reduce the footprint of the solution, but it also reduces the inductance that you have between the driver and the VCSEL. And so in the module, integrated module that's been developed by Osram, rise times actually substantially less than 500 picoseconds have been demonstrated. I think we've seen 200 picosecond rise times. But eye safety has come up previously in this meeting, and so to address that, what's incorporated into the module is also a photodetector for being able to monitor the output power, as well as an interlock that would measure or would detect if, for instance, the lid were to fall off of the module. And of course, there's a diffuser or an optic element in the lid that creates the desired field of view. And so these are being shipped now in some Android-based phones in significant volumes. Another development over the past year has been in a multi-junction VCSEL. And this has really got benefits across the board of the applications, but it's particularly useful at the LiDAR end of the time of flight range where you need a lot of power. And this is not a new idea. People have talked about this for a long time, but it can be difficult to implement. And so we have some recent results that are very promising. The VCSEL is pretty close to standard. Of course, it has a top mirror and a bottom mirror and an active region in between. The difference is that there are, instead of a single PN junction, there are multiple forward bias PN junctions to sort of multiply the amount of output power that one can achieve. And in between the forward bias junctions, you need tunnel junctions, which are now reverse biased. And because of the high doping in those tunnel junctions, you can, they have a very low breakdown voltage. And so you can get current passing through those in a way that looks almost ohmic. So if you could go to the next slide. Let's see. So here are some results from some multi-junction VCSELs. Like across the top, we have the performance attributes comparison of a single junction, 3 junctions, and 5 junctions. So on the left is plotted output power versus current. And you can see that you really do multiply, for a given current, you really do multiply the output power. In fact, it's basically proportional to the number of junctions in the device. So for example, at 8 milliamps for a single junction, you see maybe 7 or 8 milliwatts of output power. At a 5 junction device, that's up to 35 milliwatts. But of course, it has to come at a cost. You've added additional junctions in your device, and so that adds voltage. But we also see an overall power conversion efficiency advantage from the structure. And we have seen in excess of 60%, 60, electrical to optical power conversion from the structures. Now the data on the top is from a single VCSEL that is tested CW at room temperature. One can then take this kind of structure and put it into an array, just like you can with a single junction. And the data on the bottom shows the kind of pulse performance that has been achieved. So it's a chip that's 940 nanometers, slightly less than a millimeter square, pulsed with 3.6 nanosecond pulses, a 0.1% duty cycle. And from this chip, we've seen peak powers of this is a triple junction, peak powers of 147 watts for a 64 amp peak current. And given the active area, that's about the equivalent of 281 watts per square millimeter. So this starts to get us into the range that becomes interesting for LiDAR and external sensing in automotive. So, this is just kind of a summary of how the applications are driving innovation in the VCSEL area right now. Thanks.
Thank you very much, Mary. Sorry, it happened the same to me as happened to Jörg. I couldn't find the button. I got too excited with your presentation. Meeting you last year and also getting the chance to know you better in the interview, that was one of the highlights of 2019. You are already an expert, 1 year already an expert on the EPIC community. So what can you do for them? What can they do for you?
Well, as Julien said, we're always happy to provide VCSELs to people. And kind of responding to Jabil, there are cases where we're certainly open to doing custom designs, but it has to be a good business case. It either needs to be some high value product or a high volume. I think in the area that I talked about, the high pulse power for LiDAR, there's a real need for testing. It would be nice if there were some turnkey, flexible testing systems for doing this pulse testing. I get annoyed. Seems like every time we have a different combination of pulse width and current, somebody needs a new pulse generator, has to buy a new one. Optics continues to be, a challenge for these integrated modules. We need high performance, we need high temperature, the ability for the optics to survive solder reflow, but of course we want it to cost nothing at the same time. So I know that's a...
Mary, you don't know what you just did. You asked for a challenge to help you with the testing and to help you with the micro optics. Be ready for the amount of introductions I'm about to make. But we have a few questions here now. We have one from my friend Julien. Julien, what's your question?
Yeah, my question is, do you see that the stacked active regions with the tunnel junction is better suited for DTOF than for ITOF, or you think it's across the board that it's applicable?
It certainly is very beneficial for DTOF, but I think we see some advantages for ITOF as well. You know, you can get more power out of a smaller area. It's you know, also a lower current can help to reduce the size of the driver that's required. The only issue is that often in consumer systems, you have a limit on the voltage that you can use. So it may limit you to 2 junctions or maybe 3.
We have a further question. We go to Texas Instruments. Benji and Fang, thank you very much for joining this afternoon. This is your first ever EPIC meeting on VCSELs. What's your question?
So my question is about the thermal performance and also the reliability performance. Yeah, is there any reliability data or concern here? Because here we have multi-junctions in the VCSEL.
So again, the key, as someone earlier mentioned, one of the advantages of using the multi-junction and direct TOF is that you can minimize, not completely eliminate, but minimize the thermal effects. You know, your average power dissipation is modest compared to the peak power. We are doing, you know, in the middle of reliability evaluation or the qualification of these devices, and so far we don't see any big issues with reliability. I don't think we have data that we can share quite yet, but you know, we will when it's ready. With any VCSEL, you know, you always have to understand what are the limits of how far you can go. There will always, you know, you can always specify a range where the VCSELs will be very reliable, but there's always a point where you've pushed it too far and you will have gotten into a different failure regime and the devices will fail. So, you know, I think what we're doing is pushing the limits of what peak power we can achieve with good reliability, but we're understanding the trade-offs right now.
We have a further question all the way from ST Microelectronics. Do you have any plan to produce long wavelength VCSELs? And by long wavelength, he means more than 1 micrometer.
Yes. It's also something that we're looking at. You know, I think actually that's an area where Vixar could also use some help, which is to understand what the whole system looks like. You know, the question I have, if you're talking about 3D sensing, is, well, what is the camera? How much does it cost? You know, and if you could do 3D sensing at long wavelength, would the cost structure allow you to do it in consumer? Is it only going to be used in industrial or perhaps automotive? You know, I'm sure that the VCSELs, as Vertilas has already shown us, the VCSELs can be done, but it's the overall system, you know, what's the right system answer that I'm concerned about right now.
So I'm going to introduce you to my friend from ST Microelectronics, Eric Masaleirat, because he's very interested in this particular cooperation. And we go to Sumitomo. Sumitomo has a question, Yoshiaki-san. How is the output power in CW mode?
Of the multi-junction VCSELs?
I guess so.
Yes, I kind of, with all of these arrays, you know, I showed you data actually for a single VCSEL operated CW, and there's, you know, well, you saw the results, but when you put them in an array, there's always a thermal crosstalk issue that you're packing a lot of VCSELs, and certainly CW, the output power is much reduced in an array. And I don't really think that that's the ideal way to operate the multi-junction VCSELs, or the way that they really provide you a lot of benefit. It's really when you need high peak power that there's a benefit.
You will see. You're going to be ready to see something very, very, very special. The next presentation is from a company in the computer vision sector, PROPHESEE. I went to visit them in Paris and I got goosebumps with the demonstrator. And their end goal is to give vision to the blind. I think I raised the expectations not even high enough for PROPHESEE. Thank you very much, Simone, for being with us today. Tell us how PROPHESEE is going to revolutionize the world, and also tell us how the rest of us can help you do so. The floor and the attention of everyone is yours.
Thank you very much, Jose. Can you hear me?
Loud and clear.
Good. So let me share my presentation. Can you see the screen?
It's coming, it's here.
Okay. So thank you very much for the introduction, and thank you for having us here with you. We are not a VCSEL company, so you may wonder why we are here, and I'll try to explain the why now. For those who doesn't know us, PROPHESEE is a company which is headquartered in Paris. We design neuromorphic sensors and the artificial intelligence algorithm that couples with those sensors. A neuromorphic sensor, what it is also known, maybe you heard about it, as event-based sensor. And the event-based sensors are designed to mimic the human retina, which means that every pixel in the sensor is independent and activates itself intelligently and asynchronously, depending on the number of photons that are present in the scenes. Basically, what triggers this pixel is a change in contrast or light intensity. So as you see here in this sketch, we have photon incoming into a photodiodes. And then we have basically a sort of a comparator, and then you have a spikes only when there is a change in contrast. The threshold is also updated. So for example, if your light follows this, let's say, trend, you have spikes every time you have a relative change, for example, 15% in the light that hit the pixel. The output of the sensor, it is something like that looks like this picture. So basically, you don't see anything where there is no change, while you see points or events where there is a change. The change can be either a positive or negative, and we map that with a color, so you see white and black dots. As you may understand, this is a way to mimic the retina, and basically it's a way to automatically extract what is relevant in the scene. Obviously, if you are interested in looking at something that changes over time, because if everything is static, then there is no point. There are other benefits. The pixels are very fast, so our time resolution goes down to 1 microsecond. We don't have any more exposure time, and we don't have a frame rate. So basically, we are not blind in between the two frames. Also, by construction, the pixel allows for a very high dynamic range, more than 120 dB. And we tested the low light performance. The low light cutoff is at around 0.4, 0.7 millilux. Like I said, since we are basically extracting only what is relevant in the scenes, we also generate less data than a standard frame-based sensor. So why are we presenting in this webinar? Basically because there are many applications for this technology, but if you combine this MetaVision sensor with a VCSEL projector, here you come to play, we can basically realize a novel structure light 3D sensor. The applications, so we switch to the neuromorphic sensing in this case, are basically high precision depth sensing, which is also very fast, roughly 50x faster than a standard structure light frame-based system or time of flight. This has many applications. We already seen in other presentation, for example, nowadays the biometry to unlock the phones or for payments. So from faces camera, we can also imagine in near future to have a virtual chat room. So not only video like this, but with a 3D presence in the room. We can use these to do gesture control, but also to do 3D awareness, or if you want medium range 3D reconstruction that can be used by robots or appliances in the home, to navigate or to recognize you. So in these slides, you see a few examples of the output of our sensor. The top left is a 3D reconstruction of a face, a colleague face, actually, with a mask, because we are compliant with the COVID regulations. You can also see an example of 3D reconstruction of a marble circuit. You can notice the details that we were able to capture. Unfortunately, we were not allowed to put video, but this is also nice because this basically game has the balls that flows at a certain speed around, and we can follow them real time. I also want to point out that the output of despite the fact that the event-based sensor are not standard, the output of the structure light event-based is actually a standard 3D point of cloud. And here in the bottom, you see a reconstruction using kinetic fusion. So we took our output and we plugged into an existing software, and it's basically plug and play. So why we want to target, let's say, this solution, this application? Basically because we think we can break the trade-off between the exposure time, the accuracy, and the robustness that is basically present in all the 3D system, either stereo, active or passive, time of flight, and standard structure light with frame-based. I'm not going into the details on how we do it, because this is proprietary, but if you are interested, you can definitely get in contact with me. We can sign an NDA and we can show you everything. But the basic concept is that, like in structure light, we project a pattern. So there is a triangulation, like was shown 2 or 3 presentations before. But the pattern is not, in this case, is not static. The pattern is a modulated in time pattern. And thanks to the fact that we are very good in capturing what is moving in time, we can recognize this pattern. And from this, we can reconstruct we can triangulate and reconstruct the 3D. Today, we can offer basically state-of-the-art accuracy with respect to a structure light system. And if you are familiar with 3D system, you know that is structure light for, let's say, short range. It's one of the best in terms of accuracy. We can speed up the acquisition time by 50x. Typically, we can go to 1 millisecond for the full 3D point of cloud. We can reduce a lot the software complexity because we don't have to match the pattern in a post-process mode. Ideally, we can match basically the IDs of this pattern inside the sensor directly. There is no motion blur when we capture the 3D scene because we are very fast in the acquisition. And we can also be compatible with outdoor if we use very fast pulses with high power, while the energy still be compatible with iSafe. So why we're here? We're here because we do design sensor and we produce the algorithm. What we don't do, and we are not expert, is in VCSEL. So we thought it was a nice idea to present in this webinar, and thanks Jose for letting us present. We are looking for a partner or a supplier of a VCSEL that are relatively high power. Now we don't need 140 watts with fast pulses in the order of microsecond and with a wavelength that is in the 940 nanometer space. And with this, that's it. I'm available for all the questions you may want to ask.
Okay, thank you very much, Simone. So, okay, you already said what do you need from these companies. We have questions here. Simon from Jabil, do you have a question?
Yes, I do. It's actually 2 questions. What's the sensor size?
Mm-hmm. Okay, it depends on the generation. The latest we have, it has been published this year at the ISSCC. and the size is 1 million pixel for less than 1.5 inch.
Okay. And second question is, let's say the level of maturity. Is this already a mass production or off-the-shelf device available, or is it still under development? Where are you on that?
This is a good question. We actually have 4 generations of the sensor. The generation 3, which is a VGA, bigger, much bigger. It's a 2/3 of inch, 3/4 inch to be precise. This is available and in mass production, so you can order it in quantity. The generation 4, which is the one we're using for structure light and million pixel, the most advanced we have. We develop it in a collaboration with Sony. The one we have is the engineering sample. Actually, the test chip, the engineering sample will be available end of this year. And will be available also in small quantity. The mass production is foreseen to happen end of 2021.
Okay. Thank you.
Okay, thank you. And well, very nice that you raise the question of the topic of going to large volumes, because we have here in the room a few of the most important automation companies in Europe. So maybe Tobias from Isemtech, maybe it's a good moment for you to explain what are the capabilities of your company and what are you looking for in this meeting. Tobias, you are here, right?
Yes, I am. Thank you. Thanks, Anna. I needed to unmute myself. Yeah, I think that was a very, very interesting presentation, and to me, honestly speaking, very new, so highly interesting. Yes, and we are, just as Anna said, an automation company from Aachen, and we have a very flexible and open source assembly machine platform, which you can use to implement all kinds of new sensors for active alignment, basically, ultra precision alignment of optical systems. And additionally, we offer a combined business model. So basically the job shop manufacturing, prototyping, and at the end of the day, also, of course, volume production equipment. And so whenever there's a new challenge, some new system needs to be assembled, you don't really know yet which sensors to use, how the metrology system looks like, that would be something we can help with. And we're very happy to do so. So serving all kinds of different markets. And yeah, to me, this is like looking what's happening in the European photonic market. So this is another great meeting. And I've seen a lot of very interesting things. Thanks a lot.
Thank you, Tobias. And well, and also talking about automation, we have here Maurizio from Touchless Automation. They are developing a super cool technology. Maybe Maurizio, would you like to explain a little bit about this?
Yes, hi. Thank you for calling. Yes, we are actually quite new on the market. What we do is that we are able to do some of the crucial operations, for instance, die ejection, so from adhesive tape, without touching the part. So we have a combination of forces that allows to levitate the component underneath the tip of the tool. So we can do machines that are actually able to pick up, sort them with visual inspection, the components, but every time you don't touch the front surface. So if you have something very delicate like your application, that might be valuable.
Okay, thank you very much. And then we have, okay, well, I saw that we have a question from Julien, Boucart, 26, but well, maybe you can make the question anyway, because our people in YouTube will be interested as well.
Yeah, I was asking what was the pixel size, and actually I just realized as well with the idea that was described, it sounds to me like the VCSEL array you're looking for needs to be individually addressable. Is that correct?
Yes and no. We need, let's say, portion of the array to be activated. So not the full array to be activated at the same time. The exact strategies, contact me in private.
Okay, thank you.
I had the luck of contacting you private, and I've been amazed with the kind of things you can do. Also amazed with the kind of things that touchless automation can do. Did you hear right? They can actually levitate micro optics, pick and place without touching. It's frankly amazing. Looks like magic. But Simone, I have a question from the YouTube universe. ST Microelectronics, one of your future customers, believe me. Is your 3D sensing system eye safe?
We want to be eye safe, definitely yes. So the combination of power and short, let's say, the length of the pulse, we will need to be in the eye safe region, yes.
Back to you, Anna.
Sorry. Okay, I think there are no more questions or comments. Okay. So let's move ahead in the program. I have the great pleasure to introduce you, Ignazio Piacentini from Ficontec. So yes, Ignazio, if you want, you can share your screen. You are there, right? I don't really see.
Yeah.
Very good. Now I see the. Very good. If you can go to presentation mode.
Just a second. Do you have it now?
Yes, perfect.
So you can hear me. Well, thank you for introducing me, Anna, and good afternoon, everyone. It's a pleasure meeting you again. This is my first time in the last 10 years or so that I've not been traveling for 3 months, and I'm still stuck in Milan, so kind of a war zone area. So very soon, I guess I will resume some traveling. So thank you for inviting me. We've been listening to a lot of stories of beautiful devices, and again, I will be talking about automation and specifically about automating testing. So I have only 6 minutes, so I need to go pretty fast. Let's get going. And if you wonder what the little red devil is doing in the picture of the VCSEL, just query me after the presentation. So about the company, I think I will not really waste much time. We are better known for assembly than testing, but we do also quite an amount of testing. And the only remark about this picture is that my title has changed, and I'm no longer director of business development, but I've become very recently principal of photonics testing. It's a kind of a, let's say, a pre-retirement gift of my CEO to allow me to do a bit of engineering as well as business. So let's move on. So the topic of today was actually design, fabrication, and packaging. So I did not really bother Jose, but I think it missed testing there. And if you talk about volume application, then we need to talk about wafer level testing and high volume testing. VCSELs are used in many different applications. I only take two far apart for size and maybe current. One is Datacom Telecom, VCSELs on 250 micron pitch. The other one is a module for smart illumination, so a cluster of high power VCSELs, and there are many more applications in between. So talking about testing, if you consider that now you can get a 6-inch gallium arsenide wafer with a 250 micron pitch, you're talking about 250,000 VCSEL per wafer. Quite daunting number. And cost and speed become, of course, a major issue in the whole business of VCSEL. So, and testing what? Well, differentiating between R&D and production. Testing in production is a necessary evil. So you want to test as much as you want in R&D and as the least that you need in production. Primarily, you test LIV and spectral properties. but additionally, you might want to also delve into near field, far field, modulation, burn-in, and so forth. So LIV and spectral measurement can be achieved now in a few tens of milliseconds. But if you want to move reliably and accurately, and let's use the 250 micron pitch as an example, then the mechanics takes a bit longer. So if you consider 1 second for per VCSEL on a 6-inch wafer with 250,000 devices, you're talking about 70 hours per wafer. So obviously that is not the way to go. So the way to go is to go parallel. And the Ficontec has been working now for a while on multi-site optical electrical probes. And so this solution adds the overall speed that you need, remove some stress, and extend the lifetime of mechanical components, and think also of the tips of the electrical probe part. On a typical semiconductor wafer probe, 1 million touchdown is a pretty good result, but you have a 250,000 of VCSELs, you'll be replacing your needle tips quite frequently, unless you can reduce the number of overall touchdown. So beyond the integrating sphere, we have been involved in horizontal cavity edge emitting laser for quite a while, either single emitters or bars, and typically we use an integrating sphere. But these will not really fit very well for wafer level scale testing. However, some concern were there in switching to fiber optic based pickups. We did some preliminary, what I would call a preemptive strike with the Politecnico of Milan, my hometown, and we have validated that you can really replace and calibrate against an integrated sphere for the implementation of the probe heads I've been discussing. So with the probe head, you go parallel, but this has an impact on instrumentation. Now we move the problem to cost-effective instrumentation, which means really modular instrumentation. We've been working on peaks, and peaks and VCSELs are really two different games in the overall game of photonics testing. But again, we need a better and more modular instrumentation for photonics specific testing. And my apologies to Keithley Tetronics, which are also present, because I'm only mentioning Coherent Solutions, some friends from New Zealand, National Instruments from my past, and of course, Keysight and so forth. So our goal is really to offer fully integrated wafer level testing solution, which means mechanics, probe heads, instrumentation, and of course, the user configurable software that drives it. And with this, I think I'm stopping. So I hope I raised some interest, and of course, I'm available for questions. Thank you again to all of you.
Grazie, Ignazio. You always raise a lot of interest. You are an expert on epic culture and epic collaborations. Actually, many of them started thanks to you. What can you do for them? What can they do for you?
Well, I think I was expecting your question because it's always the same, so I'm pretty used to it. So what we can do, we can test your devices, or rather we can build the machines to test your devices. We are not going to test them ourselves. We're going to give you fast machine to test them. What can you do for us? Well, right now I'm trying to, let's say, optimize some of the ideas that go into the probe head. The mechanics is, for us, fairly simple. We've been doing precision mechanics for 20 years. The instrumentation, it's a matter of getting the interest of some vendors and optimizing the front end. What you can really do for us is to help us harmonize, collect ideas, and provide a supply chain for the probe head, because the probe head needs to be adapted to different devices, very much the same that happens in a conventional semicon. Conventional semicon, when you get a new wafer, you do a new tape layout, you start thinking about probing. So collecting information from you will optimize our design, will make our machines faster and more cost effective.
You have been fantastic on that, and there's so many collaborations starting with Ficontec in EPIC. We have two questions. The first one is from Yumikor.
Hi. I have a question for you, Ignazio. Germanium is, we are making germanium semiconductor wafers, and basically at this moment, there's some industrial cooperation going on. I cannot go into details on trying to do VCSELs on germanium, and germanium can be go into 8-inch and 12-inch basically.
Yeah.
In comparison to gallium arsenide relatively easily. Of course, you have to look at the whole supply chain, and also the testing is an important element. Would you be able to do 8-inch testing and even going beyond that?
I think we can. And in fact, I've been mentioning 3, 4-inch and 6-inch for VCSELs, but for PICs, we are already supply machine for 8-inch and 12-inch wafer. So PICs nowadays are really produced mostly on 12-inch full-size wafers. I'll be interested to hear from you. What are your specific needs on your material?
That's wonderful to hear. Thank you.
Thank you.
We have a further question. We go to beautiful Stuttgart. We go to Björn Hoffmann from RoodMicrotec. What's your question?
First of all, very interesting talk, Ignazio. So you are doing a great job there. My question is, do you also build systems for reliability tests on wafer level? So like burn-in, HTOL, or similar?
Well, I should answer no, but I'll be interested to hear more, because actually a lot of the technology we use will be, when you talk about burn-in, are you talking about wafer level burn-in or large scale? I mean, on single-layer devices, burn-in is reasonably straightforward. Where it comes, where the problem really arises is when the number of devices really go up in numbers. Then the major issue is power dissipation. How do you evacuate the power you are applying to the full design? So I don't really want to discuss further here, because I think we'll be running out of time, but I'll really be interested to also address your question separately. Thank you for asking. Very interesting question.
Oh, if you don't know each other, you definitely need to collaborate. RoodMicrotec is one of our key members in testing. You will see his presentation later. We go to Stephanie Blackett from Plasma Technology. What is your question?
Sorry, I had to unmute. So thank you. So thank you for a great talk. My question is really for wafer level testing. So not sure whether you could answer, but I'm guessing that with time, as the manufacturing process matures and the yield improve, we can expect that VCSEL manufacturers might not be checking the full area of the wafer. And instead of doing 100% testing, they might shift to 90 to 80 or to 70% testing. So could you maybe share whether you've seen a trend towards a reduction of that testing percentage on the wafer level?
I guess I can comment. Right now, my real headache is to test efficiently 100%. Christian from Vertilas was mentioning 40 VCSELs on a fairly complex transceiver being designed and built by VTT. For this type of application, the 100% testing today is definitely a must. That is what is required from us. If in the sort of a volume process, we'll be able to remove some of the testing, and there are a number of tricks to that, then that means that we will relax a bit on the way we build the machine. So for sure, going from 100% testing to a reduced testing will certainly be a push from the manufacturer, because as said before, testing is a necessary evil in the production. So
very good. Yeah, thank you very much. And I'm going to introduce you to a few friends, because today we talk about testing. It was fantastic, but I also want to talk a bit about the micro-optics revolution that Europe is living. And I'm going to go to Denmark. I'm going to go to the company NIL Technology. Thank you very much, Alicia, for being with us this afternoon. How are you doing?
Thank you. I'm doing fine.
Alicia, I want everyone in the room to know what NILT does in 1 minute. Do you think that's possible?
I think so, yeah. We do advanced optics. So we're experts in doing diffractive optical elements or metastructures. We can do design, we can do the mastering, and also the replication and prototyping.
Thank you very much. It is one of the key partners that you have in Europe, and I would like to remind, Europe is living now a huge micro-optics revolution with companies like Icon Photonics, like SUS Micro-Optics, like EVG. You need micro-optics, either free-form or flat. Don't go any further. We have the best technologies here. And with this, I would like to go now to continue in the field of testing. It's one of the biggest challenges in the supply chain, and today we're going to solve it, especially with the next two presentations. We go first to Ophir Spiricon. Thank you very much, Simone, for being with us this afternoon. Tell us how the rest of the supply chain can use you to test in volume production. The floor is yours.
Thank you, Jose. Thank you. Hello, Anna. Hello, Jose. Hello, everybody. So I'm also glad to be here with you today. It's been a really nice afternoon and lots of interesting applications. So my goal is today to shortly present you what we do and how can we help you and how can you help us. So I will just share my screen. I hope you see it.
Crystal clear.
Okay. Now it's even better. So in really shortly, I would just like to mention, so the Ophir is part of the MKS Instruments, which is a global provider of instruments and process control solutions. And Ophir has been in laser measurement business for almost 45 years. So the portfolio consists of the laser and LED measurement products, so sensors and imaging, but also like other high performance CR visible optical elements, and also the all replacement and OEM quality optics for CH2 or other high power fiber laser materials. So in the laser world, we have sensors from femtowatt to 100 kilowatt lasers, as well as sensoring and imaging. And we are also being more and more involved in testing for VCSELs. And the main important points that we want to address, because we think that sensors and imaging is also one of the main forces behind the search of the research and use of VCSELs. And as the VCSELs are becoming more competent and powerful, I think the key sticking points remains, and these are eye safety, the energy efficiency, and of course, optimal beam and power, and beam profiling. So at Ophir, we are saying that to stay within these safety limits, for example, for eye safety, of course, it's really needed to precisely determine the average power and pulsed energy. So in order to minimize the consumption, those laser beam power, the profile, noise, and everything, all the other parameters has to be really tested to ensure that they strictly comply with all the specifications. So how to choose the optimal technology for measuring the VCSELs? That's the main question. And I think it's important to understand the measurement principles we want to employ, and of course, the boundary conditions that apply at testing. And of course, VCSELs are often operated in pulsed mode, and of course, passive or scanning optics can be also as well used. So these are all the important factors contributing to the choice of the real measurement system. So at Ophir, for power measurement, we are offering from integrating spheres or with different wavelengths for all kind of, from 600 to up to 1,500, 600. And of course, also the special adapters can be used for wider beam angles. So up to 60, 50 degrees, but we have also special gold-plated adapters for up to 170 degrees beam angles of the light source. So the power ranges for integrating spheres, they range from few microwatts to 30 watts. But of course, we can also use the thermopile sensors for the VCSELs that could be used also with flex spectral sensitivity. So what I would like to mention that we are having also pulse characterization, which I will talk more on the next two slides. And one other thing, next to average powers and also the power energy, also the beam form of the VCSEL source is really important. And I think this geometry of the
the beam is really essential to find out the best optimal solution we're actually looking for. And here I would like to mention different options that we're offering at Ophir. So we are offering either near field beam profiling. So with a microscope lens, we can actually get all the precise pictures of the VCSELs from close up. And we offer also the far field beam profiling. So either directly, where the laser beam is directly pictured on the CCD camera, or indirectly. So this second type is specially used for VCSELs, and we have a laser beam that is actually projected on some diffuser, and with a special lens we can analyze the beam heading to the camera. Of course, the beam size, beam quality, divergence in real time, and beam shape, they're all equally important. In the next slide, I would like to mention one of our latest solutions, which is a small integrating sphere sensor, which allows really multifunctional functionality, because the 3 different measurements can be simultaneously performed. So we can measure power, we can detect the pulse shape, so the characterization of the pulse shapes with the fast photodiodes, and also the spectrometer can be easily connected to the system via SMA fiber adapter. So we are really know at Ophir that calibration and accuracy are the main points. So we can really well calibrate the slow photodiode attached to the sensor. And with this one, we allow to calibrate the fast photodiodes. So with the design of this 1.5 integrating sphere, of course, super fast rise and fall times can be achieved. And sorry, one too fast. The small, so the quite large aperture of 2 centimeters also allow working at some distance. And with this sphere, the divergent angles for the VCSEL lasers up to 60 degrees can be well measured. So what do we offer at Ophir? What I would like to mention is that our range of measurement sensors goes from power measurement to fast pulse characterization up to beam profiling. And the thing we are searching and looking for is we would like to have further input and feedback from you. So from VCSEL manufacturers, the system integrators, end users. So about the exact measurement requirements that you have. And we will be really interested to this strategic partnership to develop together the innovative solutions that you need. So, and I think there are significant opportunities that require these cooperative efforts between us to find these appropriate solutions. So that's all from my side. Here's my contact data, and I will be really looking forward to hear more from all of you. Thank you.
Okay, thank you very much, Simon. Very nice presentation. So, okay, you already said what are you looking for, but then let's elaborate the question. With which companies would you like to have a follow-up after this meeting? Which kind?
So, yeah, I think for us, all kind of partners are really interesting. It's either the system integrators, either VCSEL manufacturers. So testing on the wafer level, then testing on the system level, and also testing for the end user level when the VCSEL is already applied. So all those 3 points for us, we have quite some experience and a lot of experience in the laser world, but in the more divergent light sources as VCSELs, I think there is still much more to explore and to find out. And here are we actually open for all part of the partners on that would like to need our help to help them, and we would be actually more than welcome to cooperate.
Okay, very good. So let's explore who we have
Thank
here.
you.
I think we have Yaoi from Mellanox. Yaoi, are you here? From Mellanox? Okay, maybe not. I cannot. I couldn't see him just 1 second ago, but not. Ah, yes. Yaoi, can you unmute yourself? Okay.
Hello?
Okay, now. Yes. Now, hello, Yaoi. Maybe you can comment about what are the interests of Mellanox in this meeting? What are you looking for? What kind of collaborations?
Mellanox traditionally has a product line with VCSEL-based transistors, optical transistors. So we are definitely interested to the datacom VCSELs and the related works around that. So from VCSEL all the way through to test and to the production line. Yes.
Do you see any potential collaboration with any of the companies in the room?
Yeah, sure. I think I recognize a lot of familiar face, so here I already have all the top vendors in Europe, right?
Yes, I think so. Okay, just send me an email if you want some kind of introduction after the meeting. And then, and then also I would like to comment because, well, yes, we have been talking about the testing, wafer level testing. But what about the flip chip? So maybe it's the moment, Herman from Ficontec. Would you like to comment about the capabilities of Ficontec and what kind of collaborations are you looking for?
Hello, and thank you for asking. Well, actually, I'm joining this meeting to learn more a little bit about the latest trends in VCSEL technology. And of course, we are in some public funded programs together with some of the others here in the meeting room. And well, what we are looking for basically is always companies that are at the forefront of technology and are looking for new ways, new technologies, trying to assemble their modules. So VCSEL is one of our daily business to bond VCSELs. So all the companies that are looking for someone who, a supplier actually, who can supply equipment in the sub-micrometer range to bond VCSELs actually is very welcome to talk to us. I saw already a few very interesting presentations, took some notes, and also sent out some private messages, and hope to stay in touch. So wishing you all a very nice weekend then, and thank you for having me here.
Thank you very much, Herman. Well, thank you, in fact, to you for participating in this meeting. Okay, and also there is a company, Ulight, here, right? Guido? Are you here? Would you like to comment about what are the Ulight capabilities and what are you looking for in this meeting? Okay, so well, maybe we can come back later. Okay, with Guido. Okay, so more questions for Ophir. Okay, so if not, let's move ahead in the program. So next speaker is Björn Hoffmann from RoodMicrotec. So Björn, if you can share your screen. Okay, very good. And now if you can go to presentation mode.
All right. So since this is my first presentation at an EPIC meeting, I was in Stuttgart at the VCSEL meeting, but that was on too short notice to give a talk. So I'm going to introduce RoodMicrotec quickly. We are located in Stuttgart and Germany. We have around about 100 employees, and we have 50 years of experience as a service supplier for semiconductor parts and also for testing. So we do a lot of wafer testing, reliability testing, qualifications, failure analysis, and so on. So this is our core business. Our focus is on automotive, industrial, high-rel applications, and also datacom. One of our business models is the supply chain management, in which we cover the complete supply chain, as you can see here on the right, from an ASIC design across the wafer manufacturing, the wafer test, the assembly and packaging, final test, qualification related to, for example, automotive standards, and the whole logistics. So this is something that covers all that we offer. And we have also, this is why we are here today, we have a strong background in datacom qualification because our company in Stuttgart has a Alcatel history. So many people and equipment and so on is coming from Alcatel. So we have a good know-how there. Our labs are certified according to ISO 9001, and we are also an accredited lab. So we definitely have top quality services that we can offer to you. So going to the services my department is offering, I'm not mentioning everything here. You can read it later on, but in general, we can cover most of the Telcordia GR468 requirements for reliability tests on optical components. So, and some parts that we have here, for example, is we have a dedicated live test system from Yellow. I guess you remember this cup from Yellow that Jose often has. We have several humidity chambers to perform temperature humidity biased or biased damp heat is a synonym. So for example, what you typically do there is 1,000 hours at 85 degrees C and 85% relative humidity. This is a very stressful test for devices. They are degrading very quickly. And this is what we typically do on VCSELs or photodiodes or laser diodes. Especially for photodiodes, we offer high temperature reverse bias tests. This is typically running for 1,000 or 2,000 hours at up to 175 or even 200 degrees C. A very new development that we now have is a HTOL test for electromodulated edge-emitting devices. So this is a pretty complex topic because you need to drive the lasers and you also need to control the modulator, and that all needs to go into an oven. It has a lot of temperature that is also coming from the devices. So this is something that we are working on at the moment. Then what's also part of the Telcordia are things like temperature cycling. ESD tests is something that we have not talked about today. This is also what we offer. So the human body model or machine model tests. Our failure analysis lab is able to perform die shear tests and wire bond strength tests. And also in my department, we have a lab for mechanical shock and vibration tests. So if you need to shake something really hard or vibrate it, we can do those tests also according to all the relevant standards. And of course, we have all the characterization equipment, and I want to focus on the last 2 points because we are also able to perform high safety estimations or evaluations, and we can also perform laser classifications. So if you need something like that, we could be your partner. I want to focus on our specialty. So we are not only doing these standard tests, but one of our really strong points is that we can design custom electronics or adaptive holders. We have intelligent test programs that are really tailored to your demands. So we are working together with several well-known datacom players. And I just want to give you a few examples. For example, for VCSEL THB tests, where the devices degrade very fast, we have developed self-stabilizing current sources. So they always keep their current at, for example, 12 milliamp, even though the devices are degrading. And this is pretty helpful. And we can put up to 128 VCSELs on one PCB. And this is then coupled with 8 current sources. Recently, we have modified a Newport laser live test system to enable the control of the modulator. So you can see it here on the right. We have the rack with the Newport live test system, and in the bottom is our own equipment with the power sources for the modulators. And another thing that we have is we have put a photodiode on a XY scanning system, put all into Lightroom, not Lightroom, LabVIEW. And now we are able to scan across arrays of devices to fully automatical do LIV characterization or spectral characterization, which is needed, for example, or especially for the THB tests. All right, so now I'm going to the two epic questions that we all have to answer. What can we do for you? So we can take care of your reliability tests, either once if you have just a capacity problem, or in a long-term partnership if you are not able to do the tests on your own, or if you are a startup and don't have the equipment at all, or so there are many different reasons why you should outsource reliability tests. A good argument for us is that we have the tailored hardware. We have a very motivated team that is working on also very specialized solutions. And what can you do for us? So definitely contact us if you need a partner for reliability testing, either these single tests, or if you need an automotive qualification like the AECQ, you can also go and contact us. And if you are developing new test scenarios or devices, just contact us if you need some help, or if we could go into a public funded project and so on. So we are always searching for partners. And the last point is, so we are very used with single emitters, but we have not so much experience so far with VCSEL arrays. And since this is a growing topic, we would love to get also into that field more. All right, so thank you for your attention. And here on the bottom is my email if you have some questions for me later on.
Okay, thank you very much, Björn. So, okay, you were quite clear with what can you do for them, what can they do for you. So then, and there is plenty of room for collaborations, I think, with the companies in the room. So let's go with a question that we have here in the room, in the Zoom room. So the question is from 3SP Technologies, from Vito. Vito, would you like to unmute yourself and make the question? Okay, Vito, I will say we have you in the room. Okay,
so he's asking for which support. I guess the substrate is meant.
Which support that performance reliability test on VCSELs? On which support? So yes.
Yes.
Yeah, so typically.
Yes.
Hello, Vito. How are you doing?
Yes, this was hi, Björn. I see the picture you put 2-3 times about the TOCAN. I was just curious to know about the support you're using. You are doing everything on TOCAN, or you variate and do a chip level, or what else?
So typically we tend to use TOCANs, especially TO, I guess 46, because that's where the modules from our yellow system are made for. So we can put around about 400 TOCANs into that live test system. And that's also why we usually put the VCSELs in the same package for the other tests too. But we also work on sub-mount level to be able to test, for example, laser diodes. So we could also think of sub-mount testing for VCSELs, but we are not doing any wafer level testing so far.
When you say wafer level, do you mean the original wafer, processed wafer, or support in the shape of wafer, where you, for example, bond the VCSEL and the chips?
So we are just focusing on small amount tests. So just a few hundred of devices. When we have to test, when we have to do, for example, 4,000 device live test or random failure test, we go to a partner that you maybe also all know, which is Argotech.
Thank you.
Okay, very good. Thank you for the question. And now, if there are no more questions, I would like to introduce you a great company from Tampere. Costris team, if you are available from Modulite, would you like to explain us what are you looking for in this meeting? What are your interests in VCSELs? Hello.
Hello. Can you hear me?
Yes, very well.
Okay, sorry, I didn't expect that.
Don't worry, maybe it's just a few, maybe you can comment about why is Modulite interested in VCSELs?
Yes, so Modulite has a long experience in manufacturing the semiconductor lasers. And then we're looking into the opportunities for expanding our portfolios and also entering the VCSEL business. And basically now we're interested in the ongoing trends in the VCSEL business.
Okay, so I hope you find this meeting very interesting, no?
Yes, it is very interesting. A lot of good speakers and presentations.
Okay, thank you. So, okay, in order to learn more about this, let's go regarding packaging, regarding micro-optics of VCSELs. We have here CSEM, Jakes. Would you like to tell us about what are the interests of CSEM in VCSELs?
Yes, thanks for the question. We are mainly using VCSELs at a specific wavelength. It's 795 nanometers for quantum sensors, mainly atomic clocks, gyroscopes, and magnetometers. And we find some of these VCSELs on the market. We've heard from Vixar and we've heard from 26. And my question is more about, these are all big market, large numbers of VCSELs to be fabricated, which interests these companies. Now our market are much smaller, and this is quite difficult to interest VCSEL providers to adapt their laser to our needs. And my question is, are there other providers of VCSEL which are oriented to niche markets? And if this is the case, then I would be really interested.
Okay, so this is a question for the VCSELs manufacturers. Someone wants to answer? I can choose it. Christian, yes, thank you. Christian, would you like to answer this question?
This is indeed a question that we get a lot, we receive a lot. So when it comes to VCSELs for atomic clocks, for example, we are needing very often only a few units. And many people tell me they don't answer the phone for less than few wafers. Christian, how do we address niche markets? Like, for example, the gas sensing in longer wavelengths, or maybe this atomic clock or quantum community. Is there a chance for these people to get just a few samples?
It's a good question. We are still also a small company, and we have our focus on dedicated projects and market segments and applications. So we have to very carefully allocate our resources to our projects and to the what we develop and what wafers we produce. Of course, we always look at the business potential, because we are a commercial company and we have to grow our revenues. So at the same time, we are very flexible. I mean, for example, we do most of our revenues today in the sensing market, which is very fragmented. So we produce over 15 different wavelengths for this market. So we can also cope with smaller projects, but overall for us the goal is it in line with our product roadmap? and what is the resource allocation. So it's an answer I cannot question really completely. I can only tell you we will look at every project, and we have to prioritize as our resources are limited. Yeah.
But Julian and Christian, I have a very simple mind. So isn't it better to sell 1 VCSEL for 10K than 10,000 VCSELs for €1?
Yes.
Well,
I think what matters is the aggregate. It's the dollar amount. And of course, if you make 1 VCSEL, the problem is that, well, you still make maybe 100,000 VCSEL because on the wafer you have more than that. So what do you do with 99,000 that are left? But in the end, it's the business case is the aggregate revenue.
Yeah.
Ivan from IQ, I'm very interested in your vision here because you have invested like crazy on getting so many reactors. I went there to Cardiff and I saw them and I got goosebumps. How do you see the challenge for the companies who don't need these large volumes, but they can enable new markets? How can they get a supply chain?
Yeah, absolutely. I mean, our investment is for volume manufacturing of VCSELs, of course. That's where the big investment is. But we still remain passionate about supplying smaller supply chains. We are involved actually. So topic of atomic clocks, for example. We are involved in quite a number of projects on atomic clocks and magnetometers and things like that within quantum technologies, but they are very much small R&D projects because the demand isn't there, of course. And you know that is funded. It happens to be UK national projects and so on at the moment, but it is something that's still on our roadmap. So we are still very much involved in that small volume manufacturing area, and very much open to anyone that's interested in those sort of novel epi designs, if you like, or applications.
I love VCSELs in mobile phones and in AR VR glasses, but we have had lots of discussion with the European Space Agency for the Skylight projects and things alike, and these are huge volumes, but they start with a few units. Imon, are you noticing that companies are trying to innovate for space and have problems to integrate VCSELs in their products?
That's true, yeah. But then the Space Agency is the place you should really start, because these are the ESA is an organization which can allow this low numbers to be evaluated fully before a larger production run might be feasible or even worthwhile.
What about the companies in the R&D side? Icon Photonics, you've been enabling packaging of VCSELs already for a few years, and now you are addressing different samples. Is it easy for you to get a few samples from companies to do the packaging with your innovative process?
No, thank you, Jose. Effectively, it's not so easy. Sometimes there is always a need of to project ourselves in the future for high volume production. So it's not so easy to get small volumes. Thank you, Jose, for this nice presentation. I have one question, if I allow me.
Of course.
For the chip makers that we have here, Julien, Christian, and Mary. What would be the challenge or the key challenge that you see for micro-optics on your point of view on the chip maker on the VCSEL side? What would be the key challenge for the micro-optics?
I can answer if you want at least my view. So on the micro-optics side, so for the consumer, we want to match again the field of view of the camera. So we want, for example, for AR, VR, very large field of illumination. And that's definitely a challenge. We want to avoid high frequency noise. We want to have as smooth a response as possible. We want to have all the power content in the illumination field and no power in the outside of the field of view of the camera. We want it to be reliable. So that means it can withstand all kinds of environment, and especially when we go to automotive applications, we want it to be very robust environmentally. But I'm not sure I answer your question. I think you might have come from another angle.
No, you answered partly, but there is definitely something to discuss because the icon photonics process for the wafer level packaging of VCSELs is super innovative. And I think there is something that you can benefit. You and Mary definitely can benefit from a discussion. I'm going to make an introduction later. But I'm interested in a friend of mine, Dirk de Man, joined the meeting today from a company AAE. And many of you don't know this company, even though it's a company very well known in the semiconductor sector. Dirk, thank you very much for joining today. Tell us why you joined a VCSEL meeting and what can you do for this community?
Thank you all for having me, and I'm overwhelmed with all the smart guys and women in this room. I feel very lucky to be listening to you guys and learning from you guys. I'm intending to learn how the market is developing, how we can be of service. There are quite a few people already attending this meeting that we are in contact with, and that we are discussing with them how we can help them to push their technical boundaries. We do that in a way that we can build machines for you that you want to scale up in. And we do that for many years in the front end of the semiconductor industry and also in the back end of the semiconductor industry for packaging and bonding and machines like that. And for me, the trends I'm investigating is how we can work smarter as a group and not a lot harder, which means more focusing on collaboration and making sure that our agile organization stays agile and other organizations become more agile too.
Okay, thank you very much, Dirk, for this introduction of your company. And now, okay, if there are not more comments for Dirk or for Björn or for the companies in the room, let's move forward with the last but not least presentation. So Hamad from Optiwave Systems. Oh, very good, you were ready.
Here you go. I'm waiting impatiently. Okay.
If you come to the presentation mode, okay, perfect. So what is yours?
Okay, so thanks, Anna and Jose, for this opportunity. Actually, I wanted to go quickly about introducing Optiwave. This is our first time to present here at EPIC, so hopefully we give more information about Optiwave and get more introduction with other companies and collaboration eventually. So Optiwave is established in 1994. It's in Ottawa, Ontario, mainly developing software for designing simulation optimization for components, systems, and network and links. Optiwave, the advantage of this software can give a competitive advantage for shortening the product time introduction through simulation, which could provide savings on cost and enhancing the productivity. In Optiwave's product is in 75 countries. We are licensing our product to over 1,000 industry-leading companies, universities, research institutions. And this is a list of different companies who are our customer. Quickly, you can go through the presentation later on. Now I'm going to talk about the main product of Optiwave. In system level, we have two main products, which is OptiSystem and OptiSpice. And then the component level, we have different products like beam propagation method, OptiFDDT, OptiFiber, OptiGrating. And newly, we're going to introduce some new software, which is coming in next month, which is called OptiInstrument, enable users to remotely control and communicate with instruments, set up parameters, do automation and testing characterization, and as well as allow users to view generated signals, extract data, and process the data remotely. So this is something coming up. Here, quickly, I'm going to go through the capabilities of OptiSystem, which is the main software which addresses the VCSEL market. We are talking about it today. OptiSystem has capability to talk to simulate optoelectronic circuits, networks, amplifiers, modulate, provides capability to advanced modulation schemes, wireless communication systems. It can do sensors, as well as the other software, which is doing the finite time difference methods, beam propagation method, OptiGrating, and OptiFiber, the mode solving methods. for photonic crystal fibers and other types. In capabilities for OptiSystem in wireless communication market, we address the Li-Fi, free space optics, visible light communication. So all of these system can be simulated in OptiSystem software. And the things which is also important here, we offer lots of capabilities in microwave photonics for modulators, lasers, filters, designs, and characterization. In the LiDAR market application, we offer different simulations for time of flight range measurements, as well as the frequency modulation continuous wave methods. We offer sensors for using gratings or PHY OTDR, gyroscopes, OTDRs. We offer DSP components which can do signal processing for the systems, plus the advanced modulation. For the sake of this workshop or meeting here, the VCSEL component offer, we have 4 different components. One of them is for single mode application, and then others for multi-mode applications. For single mode application, we have the VCSEL laser, which includes thermal models, parameter fitting based on measure of Li IV curves. So you can extract the data from measurements and then plug that in the components, which is shown here. And then eventually you can do the simulation in a system level. In the VCSEL laser, there is another component called measured. It has more functionality beside the ones described here, and allows the user to extract laser rate parameters from measured threshold current, optical power, resonance frequency, and damping factors. The other types of VCSELs, which is for multi-mode applications, the spatial VCSELs, and it can be as well spatial temporal VCSELs, which supports 2D spatial dependent rate equations and accounts for dynamically spatial interaction between optical fields and carrier distribution in active layers. This is general view of the GUI of OptiSystem. And for example, once you double click on the component in here, you pop up a window here, which has all these parameters you can set up. You can sweep these parameters, you can optimize these parameters in your setup, and you can control load the input parameter measured data and they do simulation with the measured data. This is the other component here, and the other 2 components. And then here eventually show you some examples of OptiSystem. This is a multi-mode VCSEL used for transmission BAM signals. And then in the system here, we can show you, for example, the GUI quickly. This is the GUI, how it look like. The component, as you double click on it, you can see the parameters. You can set up thermal effects. You can set the physical dimension of the component. You can fit up parameters, load it in. If you have spatial effects, you can put the modes in LG modes or hermetic Gaussian mode, LB modes. So lots of flexibility in the model. And in this system here, you have lots of visualization. So you can see eye diagrams, you can see constellation, you can see oscilloscope, time domain, frequency domain. So lots of flexibility in the tool. And it's easy to use. It's just only dragging components from libraries here into the layout, and then basically run the calculation. We offer 30 days free trials for anyone who wants to try the software, and we are looking into collaboration with the different people in the meeting here, and to work on simulating and implementing the different software in their design and in their manufacturing floors. So this is different results for visualization. And with that, I just conclude and open for questions. Thank you.
Thank you very much for a great presentation. It's so nice to have the design companies, the optics companies, the VCSEL companies, and the users together, and so good that there are so much room for cooperation and for collaboration. The idea here is that you all got to know each other today. In 2.5 hours, so it's 5:33, we managed to get to know each other and we managed to find cooperations. So I would like to ask you the epic question. You have the whole supply chain in front of you. What can you do for them? What can they do for you?
So for us as Optiwave we wanted to collaborate with manufacturers and with design houses to be able to use our tools in their facilities to be able to simplify the designs and study the different like system parameter variation, the effects in the system levels or the component levels. So this is something which we could offer to the different companies. From our side, we like to also get the collaboration with the different, especially fabs, to get data from them and plug it into the simulation tool to tune it in case if there is some parameters to be tuned to give more realistic models for the simulation tool.
You know what? I think it's been a great meeting. I think there are a lot of cooperations to be made. I also think it's Friday, 5:30. I know that. So I'm going to tell you just what I have learned. Well, what actually more than have learned, what I think there is a lot of room still to learn. The first thing that I would like to let you know is that I think we need to continue meeting. I think we need to continue meeting in different places, and the online technology meetings are, of course, a great place for that. I also want to, let me just quickly share my screen.
You're already sharing.
Okay, thank you very much. So I would like to let you know that for me, I have seen the biggest challenges is everybody was asking for longer wavelengths beyond 1 micrometer. We had lots of questions from STMicroelectronics, from Sumitomo on the chat. They are really desperate on that. On the other one is the wafer level testing. On that, Ficontec really has positioned that there is a lot of room to cover to have an electro-optical probe that can actually do this at a speed that is demanded by this, and I think Ignazio on this is really setting up the pace for the rest of the companies to follow. Testing and reliability is a challenge, not only at wafer level, but also at die level, and especially for the applications we are targeting. And on that, I think RoodMicrotec is an epic, helping many companies as well as Ophir managing to do this. The packaging, especially the micro optics for the VCSELs, is something that we need to discuss more in depth. We are doing events only on micro optics because the push is huge, especially for the LiDAR and the automotive sector. We have actually an event on 15th of July, online meeting on ADAS plus autonomous driving. We are actually addressing this with Iveo and Valeo. Furthermore, I took here a slide from the market report of Joel that we have bought on VCSELs, and there they are talking about the key applications. And I did realize that for me, what I really see growing a lot, and thank you, PROPHESEE, for that fantastic presentation. Also, thank you to Six for mentioning it, is the structured light market. I think this is one of the booming market in the coming years. We're going to have an event only on computer vision and structured lighting, but I think this is something that we need to keep pushing and addressing the needs. And today we have from PROPHESEE some other demands on VCSELs for that particular market. Technology trends. I love the presentation from Mary, but I just love Vixar. I cannot hide it. And the multi-junction VCSEL is something out of this world. The high power short pulse demands are really key there, and the high-end small volume. We have to enable new markets with the VCSELs. Not everyone can put VCSELs in the Apple iPhone. We have to make sure we enable new markets, and that starts with accessing at the small volumes with the high-end VCSELs. I took here a little bit of a square. We are looking for VCSELs on high power, short pulses, wavelength of 940 nanometer. Jabil is doing crazy things on the camera business world, and they are looking for that. So I hope that we all give them a lot of business on that. And with this, I would like to wish all of you, my friends, a fantastic weekend and enjoy your family. If you can get out a little bit, well, if you have to stay home, there is a lot of things you can do at home. Believe me. See you soon. Bye-bye.
Bye-bye.
Thank you. Bye-bye.
Bye-bye. Bye-bye. Great meeting.
Bye.
Thank you, Björn.
Have a nice weekend. Yes.